this is a replay, and if you have any questions, put them into the chat, and we'll make sure that Elaine gets them, and they'll be answered. Also, we'll post the replay on our website, and if you're here and your question wasn't answered, go to our EAT community and interact with others. Post your question, or we'll post the replay with your answers. And so we're going to get started here in a second. Just waiting for a minute, and yeah, it'll be a minute before we get started. Once again, thank you so much for joining. This is EAT Community, and this is our weekly replay webinar. And we do have live webinars from time to time, like we had one yesterday with Dr. Wayne Durbin, and we'll have more of the live events moving forward. So check your emails to see our announcements, and also go to Elaine's website to check out what she has at the Soil Food Web System, Soil Food Web School. I'm sure you'll find a lot of valuable information. So we're getting started here. Thanks again, and here we go.
Okay.
Okay, so hey everybody, if you showed up, we're a bit early. We've got a few minutes to go, but we're just hanging out here before we get started. So I'm Raleigh Latham. I'm joined by Neil Spackman, Matt Powers, and of course the one and only Elaine Ingham. So feel free to type in where you guys are coming from. We got a little chat box, so we'd love to know where you're coming in from. So type that in the questions, and then, yeah. I'm coming from Iowa City. Neil is from Saudi Arabia. Matt's from California, and so is Elaine. So we're coming from all over the place. Okay.
Yeah, I'm actually an Oregonian, but I'm down in California, right? So the research farm that we have is in California. So I spend about 2 weeks every month here at the farm, and I spend about a week at home, and then the rest of the time I'm traveling.
Nice.
Wow.
Sort of like Neil, who's in Saudi Arabia. Oh, no, you're in Jordan right now.
No, I'm back in Saudi Arabia.
Oh, okay.
We were in Petra yesterday.
That's an amazing place. Yeah.
Yeah, it is. I noticed way more this time. I was there 6 years ago, and this year I was there just to look for water stuff, and saw some really cool things that will probably end up in a future webinar.
Yeah.
So we came back. We were in Wadi Rum this morning, looking at desert stuff and trying to catch lizards with my kids, and then drove back. We're somewhere like in the middle of Saudi Arabia, in the Tabuk region, but I've been in the car for like 9 hours today, including 3 trying to get across the border.
Well, we're glad we can make you sit down more, Neil. It's fantastic.
I'm lucky to be.
So here we go. People: Alice from Redmond, Domingo, Peter, Richard, Sandy, Marie, Mitchell, Frank, Thomas. Oh man, we're all international. Every country is represented, every state. This is great. Oregon, David from Salt Lake City. Fantastic. All right, guys. Well, we're about to get started soon. So I'm going to hand it off to Neil Spackman.
All right. I've got 2 minutes before 9 p.m. where I am, so
Okay.
that means...
We have 1 minute here. California's ahead of the curve.
We're 30 seconds ahead of you.
For all of you who were at our last webinar, we had some serious issues with our software. And so we are trying out a different system right now for this one because we had so many technical issues and so many problems. So we're working with different software this time. Hopefully it's going to be a better experience for all of you and for us as well on the behind the curtain side of things. We'd love to hear from you if you do have issues so that we can figure out what the best way is to do this. Raleigh and I are still figuring this out as we go along, and so your feedback helps us figure out how to make it better, both in terms of the technical experience as well as in terms of the content that we're putting out. That being said, I've hit 9 o'clock, so we are going to jump right into this. When you're dealing with soil, you're dealing with, a very thin layer of stuff that is responsible for all of us being alive, right? Without soil, we're not alive. And there are 3 ways of dealing with soil when you're a farmer or a homesteader or a grazer or you're dealing with land management. And those are, you use physics, you use chemistry, or you use biology. And chemistry has been the dominant mode, at least for the last 60 years. And it used to be a bit of an anthem that chemistry will make our lives better, and chemistry is, when the Green Revolution back in the 50s and 60s, chemistry was the big thing. And now biology is really starting to take over the cutting edge of this, in part because there's so little about soil that we do know, but also in part because by turning to biology to deal with our soil, we can actually do things sustainably instead of mining the earth and trying to force nature to act the way we want it to instead of cooperating with it. That being said, I'm really, really excited to have Elaine Ingham on with us because she's, I think, at the top of the game when it comes to using biology as a way of dealing with our soil. So I'm really excited to hear what she's going to say. At the same time, she offers classes online, and at the end of our presentation today, we're going to have a special offer for you through Sustainable Design Masterclass to take one of her classes. So stick around for that if you're interested, and then we're going to have a question and answer session after that short pitch, after our initial presentation. So thank you all for coming. I hope you get as much out of this as you would like, and thanks for coming to Sustainable Design Masterclass. I'm going to turn it over to Elaine and Matt.
All right. All right. So I'm here to introduce Dr. Elaine Ingham, and it is an absolute pleasure to do so because when we talk about the soil life, the soil food web, when we talk about compost tea, when we talk about composting, and we talk about testing for soil life, it's not just that Dr. Elaine Ingham is at the forefront of these things. It's not just that she is leading us. She set the tone by creating the discoveries that we are now all running on. She is the one whose research created new testing methodologies that we're all now using to verify our soil life, to verify the fertility in our soil. And it was through her PhD work, through her research and her development of all these things that, they could have come at any time, but they didn't. And it took someone like Dr. Elaine Ingham saying, why? What's going on here? Let's get in here. Let's actually figure this out. I don't take your word for it. I'm not going to just trust you. We're going to figure this out. We're going to prove it. And she took that attitude, that perspective, and applied it to the soil and applied it to gardening and farming and all this stuff. And basically, her methodology for testing opened the door for everything we know now about biological farming, everything we know now about testing for soil life. So in my mind, and for me, Dr. Elaine Ingham is where I go to learn about soil. That's who I'm asking questions from with, and that's who I'm getting the information I trust and the things I can actually go and test. Because it's one thing to have experts just tell you and just, oh no, trust me, I'm going to say it loud and I'm going to say it proud. No. It's a completely different thing where they give you the tools to verify how accurate they are, where you give them the tools to prove it on your own plot of land with your business. And Elaine Ingham has been working with people with real farms and real businesses and real soil, making real things happen for people all over the world for years now. And that's why she is at the forefront of this, because she started this revolution of the soil. And that's why I appreciate everything she does so much, because for me in my work, it's people like Elaine who are making it understandable so that I can translate that to children, families, even adults all over the world. And without someone like Elaine doing the work that she's doing, we would be poor for it all over the world. And the work she's doing today is as critical as the work she was doing 10 years ago. And it's continually improving and becoming more important, amazingly more important. So I'm so excited that so many of you are here to participate, to learn, and I hope that many of you sign up for her course and continue the learning process, because she's going to share with us tons of information, but it's just the beginning. And once you grasp it and you can implement it, you're going to see such change in your business, in your soil, in your farm, and in your life. So without any further preamble, I'm going to let you in and I'm going to let you get the information. Here we go. Here's Dr. Elaine Ingham.
Thank you so much, Matt. That's a really wonderful introduction. And, you know, and everything. The work that I've done is built on the shoulders of other scientists who have come before me. But I do take a very questioning attitude about you know, statements where it takes 100 years to build an inch of soil. Really? Is that true? Maybe if you're in the desert, that would be true. But if you start to understand what nature does, how has nature built soil in those old growth systems, in highly productive meadow situations where you can run a 100 head of cattle and keep them alive and happy on very small amounts of land, there has to be something else going on. And so if we pay attention to how Mother Nature has been doing all of these things all the way along, we can start to use the same management that nature uses to build soil, and we can build it very rapidly. I always like to tweak people who come at me with the idea that you can't build soil very rapidly, and I like to say, yes, I can. I can build you 30 feet of soil overnight. Give me the right starting materials, and I can do it. So 100 years? No. But you have to understand what you're doing. If you don't have a microscope, if you don't have any way to assess your starting materials going into that, well, really, dirt is what most people are starting out with. If you don't have a way to assess the biology that you're putting into that dirt, you're playing trial and error, and it's going to take you years to do the transition, not overnight. So that's why we really push that assessment method, and Matt is very, very correct when he says that's part of the power of this. We can teach everyone to do your own assessments, so you don't have to send a sample off and wait 2 weeks, a month for the information to come back to you to tell you what was going on in your soil a month ago. That's too long. Most of us need to know right now. So part of what I'm going to do is be showing you some of the organisms. I can't go into everything. This is way too short a period of time to do everything for you. So we're just going to get started. You'll see some of the organisms, but I do want to concentrate on examples of where we've done this transition from dirt into soil. So if we can go to the next slide. I like to go through all of the things, the major, really hugely important things that a healthy food web will do for you. I'll show you a picture of what I mean by that food web, but let's go through the important points of if you get this biology back into your soil, you will gain these functions, these abilities will come back to your dirt, because it's the biology that performs these functions. It's just like, you know, when we're talking about a business that makes a product, go ahead, try to make that product if you don't have any organisms involved in that process. It's not going to happen. It takes somebody driving the controls. It takes somebody to put the product in the box, to, you know, put the starting materials into the process line. You have to have organisms to do that. And so in the soil, who are the organisms? What are they doing? And here's the list of the important major things. So first of all, if you get the proper set of microorganisms, that food web set of organisms into your soil, those organisms grow on the surfaces of your plant. Every single nanometer of your plant will have organisms growing on it. And it is the plant itself that's putting out the food to feed those organisms, so there's a mutualism there. The plant is feeding those organisms, the beneficial organisms. As long as we make certain that those organisms are in your soil, you will have those organisms that will protect your plant against any disease, any pest, any parasite. It's as soon as you put on an inorganic fertilizer, as soon as you use a pesticide, you just killed all those beneficial organisms. You wiped out way more of the good guys than you wiped out of any bad guy you want to talk about. So it's kind of like, you know, the road to hell is paved with good intentions. So pesticide salesmen, fertilizer salesmen, they think they're doing good things. But if they really understood what they were doing to the soil, turning it into dirt, they would never recommend those things that they're recommending. So how do we get this realization back into people's minds? And that's by all of us out there doing this kind of biological agriculture, biological gardening, biological turf, biological everything, putting the biology back into our dirt and turning it back into soil. So we'll suppress diseases. You don't need pesticides. And most of the time, you're not going to need inorganic fertilizers, and there's a few more bits that I have to add to the fertilizer story. But we don't have the diseases, the pests, the parasites, so you don't need to be using those toxic chemicals in order to grow your plants. The second major thing that a healthy soil food web will do for your plant is to retain nutrients. Instead of losing all of your soluble, leachable nutrients from your soil, you need to keep those, you need to retain them, and the organisms that do that work for you have to be present in that soil. And again, they are going to be supported by the exudates, the foods that the plant puts out. Those foods will grow, help those organisms grow and retain the nutrients. Why would your plant do that? Because it knows, if you will, if I can be a little anthropomorphic here, the plant knows that it's going to need those nutrients. The plant doesn't want to have those nutrients wash out of the soil. So they're going to feed the bacteria and the fungi especially to make certain that all of those nutrients are retained in their bodies. There's no organism on this planet that has a higher concentration of all nutrients than bacteria. Fungi come a very close second. So bacteria and fungi have to be up to a minimum set of levels. There's a certain amount of biomass of those organisms have to be there in order to retain those nutrients, so you stop leaching. As soon as you stop leaching those soluble nutrients out of your soil and into your lakes and rivers and streams, into your drinking water, right there, we're going to reduce the cost of water and cleaning up water. And you will have clean water if you don't allow the leaching and the loss of all those soluble nutrients into your soil. This is how nature has done this for the last 4 billion years. Why do we think we know better than nature? That poor Mother Nature, she needs our help. She just doesn't understand how to retain nutrients in the soil. Nature doesn't understand how to cycle nutrients into a plant available form. She's only been at this for as long as plants have existed on this planet. This nutrient cycling system, this biological food web, has been present to help the plants, to help all of the organisms that we care about. So the third really important thing that a healthy food web will do for you is to make nutrients available to your plant in exactly the right form, in exactly the right amounts, at exactly the right time. So when your plant is trying to germinate, that seed germinates, it's got a massive demand for nutrients because it wants to grow all that above ground biomass. It wants to grow all those roots down into the soil. Some mechanism in that soil has to be occurring to cycle those nutrients and make them plant available. Think about any natural ecosystem that you want to consider. Old growth forest, highly productive pasture, whatever kind of ecosystem you want to envision. There's nobody out there putting on inorganic fertilizers in order to get those plants to grow. There's nobody out there putting on pesticides in order to prevent diseases and pests. And yet there are no diseases and pests. Parasites are not a factor in those natural ecosystems. Where are all the nutrients coming from? If the rate of growth of the trees in an old growth forest far exceeds every agricultural crop field, how do those trees stay alive? And they have managed to stay alive since before the time that Christ walked this earth. Now, long before the Roman Empire, those trees were growing in that old growth forest. So how did they manage to stay alive at a growth rate that far exceeds any agricultural field? More nutrients are put away into the bark, into the wood of those trees on an annual basis than any amount of nutrient removed from an agricultural field and ship it off to the market to feed people. So if an old growth forest is being more productive than any agricultural field you want to talk about, and yet nobody's putting on inorganic fertilizers, there is no need to put on pesticides, there are no weeds in that forest, can't we use that information? If we understand how nutrient cycling, if we understand these really important concepts, who is it that's doing this and how does nature do this, we can then use that management to grow our crops without the pesticides, without the toxic chemicals, without the inorganic fertilizer. Every inorganic fertilizer is a salt, and it's killing these organisms in your soil. You know, think about the chlorine and the chloramine that's coming in your water, and as you're watering your lawn, you're killing the organisms. Why do we put chlorine and chloramine into our drinking water? It's to kill microorganisms that might be growing on the pipes so that those organisms, those pathogens, don't appear in your drinking water. And yet you're using that drinking water with those toxic materials in it, and you're killing the organisms in your soil. What happens when you kill organisms in the soil? All these wonderful functions can't occur. They're not going to be happening. And so no nutrients available to your plants are going to be sick, they're going to be unhealthy, they're going to die. So we think that putting on inorganic fertilizers will help those plants. No, you're making your plants drug addicts. You're stick them in and trying to give them that IV and keep them alive, and it's not sustainable. And it has all kinds of other consequences that harm the ecosystems around you. So let's understand this natural nutrient cycling system. When we look at a plant with its root systems going down into the soil, all over the surfaces, every surface of that plant is putting out exudates that will feed these organisms in the soil. Well, great, what's an exudate? Scientific ease for, well, what is that stuff? Well, basically, exudates are made up of mostly sugar, a little bit of protein, and a little bit of carbohydrate. Oh, great, she's using the scientific terms again. What do I mean when I say, if I asked you to go into your kitchen and grab a whole huge diversity of different kinds of sugars, pull out some protein, add that into the mix, pull out some carbohydrates, what am I asking you to make? Well, sugars, brown sugar, white sugar, syrup, honey, all the different kinds of sweet things. Put a little bit of those things into your bowl. Okay, what's protein in your kitchen? Well, eggs, milk. Okay, let's put those things into this recipe. And now, what's carbohydrate in your kitchen? Well, it's flour, all the different kinds of flours. And so now what are you mixing up and what are you making? You're making cakes and cookies. So let's change that word exudate into cakes and cookies. And that's what your plant is putting out. It puts out very different kinds of cakes and cookies depending on what the plant requires. If it needs more iron today, it's going to be putting out chocolate chip cookies. Growing all those bacteria and those fungi that make the enzymes to pull that iron off the surfaces of the sand, the silt, the clay, the rocks, the pebbles, the gravel, and organic matter if you happen to have some organic matter in there. Bacteria and fungi use their enzymes to pull the nutrients that the plant is going to need, that the plant's ordered by putting out those cakes and cookies. And so they're tying up all those nutrients. They're retaining, holding, keeping those nutrients in that area right around the root system. And well, the bacteria and fungi are growing to really massive levels right around that root system there. They're protecting your root system against the diseases, pests, and parasites. So, that system works very, very well. Oh, yeah, but all we've done is retain the nutrients in the bacteria and fungi that were grown by the plant. How do you do that next step? What do you have to have in your soil to go that next step? Well, you better have some protozoa. They eat bacteria. You need some nematodes. Some of the nematodes are bacterial feeding nematodes. Some of them are fungal feeding nematodes. And so the function of these predators is to eat the bacteria and fungi around the root system of that plant. So the plants put out lots of exudates, ordered the nutrients. Yeah, the nutrients are sitting in those bacteria and fungi. And now they're going to get eaten by protozoa and nematodes, microarthropods. They also eat fungi. And so as the predators of the bacteria and fungi are eaten, the predators take the nutrients that they require, but the concentration of every nutrient is way higher in the bacteria and the fungi than in the predators. So here's the picture of the soil food web. I'm going to, in a minute, go back to that first slide. But when we're looking at the bacteria and fungi, follow the arrows here. You can see the sun at the top of that picture on the left-hand side. Photosynthesis in the plants, all the sugars produced by photosynthesis going down into the root system, and the plant then making exudates. And the arrows move right on over to bacteria and fungi. Does your plant need more bacteria or does it need more fungi? What's the proper balance to grow the plants that you want to grow? And that determines which plant is going to be selected under different conditions. So bacteria and fungi using their enzymes to store nutrients in their body. The next column then are the protozoa. The flagellates and the amoeba are the good guy protozoa. Ciliates are the, something's going wrong. So we use those as good indicators. There's your nematodes, your bacterial feeders, your fungal feeders. They're going to be eating bacteria and fungi. There's the microarthropods that eat fungi. And so in that interaction between the bacteria and fungi and their predators, nutrients are released because the nutrient concentration in the prey is so much higher, and the bacteria and fungi is so much higher than in the biomass of the predators. So right there at the root system, all the nutrients the plant requires is being released, and the plant takes up what it needs. And it says, thank you very much, guys. Now I need, instead of iron, now I need some more boron. That's what I'm lacking in now. So the plant puts out a different cake or cookie. So it puts out red velvet cake now. And so enhances the uptake of that particular nutrient. But it's getting all of them. Bacteria and fungi don't grow on boron alone. They can accumulate boron in their biomass, which is then going to be released. So you can see where there are consequences of this process going on. So nutrient cycling, that's how nature puts the proper sets of nutrients, the soluble nutrients, but only around the root system. And the plant takes up what it needs. If there is more nutrient being released than the plant needs, then the bacteria and fungi are still left, didn't get eaten by the prey. They're going to take up those soluble nutrients, hold them, retain them, keep them in the root system. So it's a system that works remarkably well, and it prevents loss of water quality. So we have to follow this approach. The thing that's going to take human beings off this planet is a lack of clean water, not a lack of food. We grow more than enough food to feed everybody on this planet. What we lack is clean water. And so we have to convert to this biologically sound, this sustainable system for growing our plants. And we can use the balance of the bacteria and fungi, protozoa, nematodes, microarthropods, to select for the particular crop species that you want to grow. And if we're setting up conditions so that just the crop plant that you want is what's going to be selected for, then weeds are no longer a problem. Weeds require a highly disturbed system. Every time you till your soil, every time you mix and churn your soil, you're slicing and dicing and crushing most of this beneficial set of organisms. And so, of course, weeds are going to become overwhelming. You're doing exactly those things that select for the weeds. Strictly bacterial-dominated soil, you are not going to be growing healthy carrots or healthy corn or healthy blueberries. We have to shift the proper biology along in that right direction. If I could go back to the first slide just really quickly. So we've talked about nutrients being made available for plants. And if you are getting this nutrient cycling put back together, there's absolutely no requirement for inorganic fertilizers. You don't even need organic fertilizers. If you're managing this system right, the residues from your crop plants, the residues from whatever you're growing on the surface of the soil will be decomposed. Any toxins that might have occurred from compaction or from having to drive your equipment through the yard, through your field to harvest, will be alleviated because those foods, those residues from your plants, will feed those organisms. As the organisms decompose that litter material, these organisms turn it all back into soil, into organic matter. So it decomposes any toxins. And the final thing really has massive consequences once we start to understand this is that these organisms build soil structure. They are what makes soil soil. If you've got dirt, I've kind of touched on this a couple of times. What's the difference between dirt and soil? Dirt is just the inorganic rock material, the mineral material. So we're talking about rocks and gravel and boulders and sand, silt, and clay. As the rocks, as the boulders are broken down into certain size fractions, and it depends on what parent material you have, how much sand, how much silt, how much clay, those balances are determined by the parent material. But who is it that does that breaking down? It's the bacteria and the fungi are the most important things. So if you want to get the nutrients that are in your soil into a plant available form, you better have bacteria and fungi because they're the ones that do most of the breakdown of rocks into sand, silt, and clay. It's the bacteria and fungi that make the enzymes that pull the nutrients, pull the nitrogen, pull the phosphorus, the sulfur, the magnesium, the calcium, the sodium, all of the different nutrients that plants require. They are what pull those nutrients out of the crystalline structure. So from now on, just take your soil chemistry reports and rip them up and throw them away, because they tell you nothing about all of the nutrients that are present in your soil. You are told to ignore all of the nutrients that are actually present in your soil. You cannot access them if you don't have the right life. So get the right life back in there, and you don't have to be buying inorganic fertilizers. If you're getting the biology set up the way it's supposed to be, you do not need pesticides. You do not need herbicides. So see how much money you could be saving? Get these organisms back into your soil. Let them do the work. They are willing organic workers. These are the real deal here. You don't have to pay them. You just have to be growing plants. And you have to manage that soil. You've got to manage the balances. So you need that microscope to be able to tell whether what you're adding is surviving when you put it into the soil. So we're building structure with these organisms. If we build structure, if we get the micro aggregates built again, if we get the macro aggregates built again, if we get all of that furniture moved around in your soil so you have large air spaces, medium air spaces, small air spaces, you have the airways and the passageways to allow water to easily and rapidly infiltrate, but then be held in all of those pores, different sizes. The water gets held in there. If we've got organic matter being decomposed by the bacteria and fungi, that organic matter holds 10 times its weight in water, all of which can become available to your plant if the root system of your plant can grow down into that soil as deep as it is possible for those roots to grow down into the soil. Most people think, they've been told, that root systems only go down the top couple inches. It's absolutely not true. And I've got some good pictures to show you as we go on through. So we reduce water use. You don't have to use as much water to grow the same amount of yield. We increase water holding capacity. We can increase rooting depth. We hold on to all of the nutrients. When your plant requires more nutrients, it tells the bacteria and fungi to get to work. That brings the protozoa, the nematodes, microarthropods into that root system. So think of how much you can reduce your costs, because you're not buying inorganic fertilizers, you're not putting out pesticides, you're not putting out herbicides. Think about the fact that you are not driving your tractor. You are not walking across your field and applying all these toxic chemicals. All of a sudden, everything becomes actually sustainable. Your job as a grower is to make sure that the biology is what it needs to be, and then you put a furrow in, drop your seeds, close that up, and let things grow. No diseases, no pests, no weeds. Maybe you have to go out there and pull a weed or two, but it's not going to be the thousands of weeds that we have in the current system of chemical agricultural production. So going on to the next slide. That's given you just a hint of how this food web works. You can see that we've talked about the root systems, that in the below ground, everything is covered. The plant is feeding those organisms to protect itself against disease. Same thing happens above ground. We need these same organisms. All of the organisms on the above ground part of your plant come from the soil. So there's the inoculum. All those cute little protozoa climb up your leaves and inoculate your above ground part. All those little nematodes, the good guy nematodes, are moving up into the top. All those microarthropods, all those insects buzzing around, all the birds, when they land, they're carrying a diversity of those organisms. And you want to make certain that your birds are coming from ecosystems that have beneficial inocula and not from a chemical agricultural field, because what's going to be on the feet of those birds coming from a chemical agricultural field? Toxic material. So we've got to expand. Everybody needs to start and then start convincing their neighbors, and we need to have these successes. We have a tab on the website, soilfoodweb.com, about different people's success stories. And you know how most farmers are. They love to tell stories about how fantastically well this has worked. Get them to write it down, get them to take pictures. Yeah, so we're doing our best to get these success stories up. As you try doing these things, please send the success stories so we can advertise, we can get the information out to everybody so that we can be sustainable and human beings might be able to hang on this planet. As we go through that food web then, bacteria and fungi eaten by the fed by the exudates both above and below ground, protecting your plant, nutrient cycling, retaining nutrients, building soil. Soil, which by definition has to have life, the proper life in it. Dirt is where you just have sand, silt, and clay. The inorganic fraction, and it's only part. Hans Jenny, the father of soil science, defined soil as being, sure, the mineral part, the sand, the silt, the clay, rocks, pebbles, but then it has to have organisms. And for those organisms to stay alive, they have to have organic matter produced by the plant. We should never have an agricultural ecosystem that doesn't have plants in it. So to have a fallow period where you don't allow any plant growth, yep, you are walking that pathway straight into addiction. The road to hell is paved with good intentions. We have to understand what we're doing, and we need to get these organisms back into that food web. So now I'd like to do some examples. So if I could have the next slide. This is to give you some references, a good place to go back to, because this is the original paper where the benefit, nutrient cycling, preventing diseases, pests, building soil structure. This is the original paper. It's an ecological monograph, so it's a very long scientific article. But for the scientists in the crowd, those people who have to have documentation of this kind of information that I'm putting out, here's the original paper that started it all. So Ingham et al. In 1986. Looking at the interactions and the fact that plant growth was much, much better where we had complex, diverse food web in the soil. Not quite so wonderful if you just have one or two components. If you have if you just have bacteria, you're not going to be growing plants. If you have just fungi, sorry, not going to be growing plants. And hopefully now you can explain to all your friends why. You got to have the whole food web. You can't just have one or two components. If you put in an inoculum that's got 5 different species of bacteria, make me laugh. That is nowhere near adequate to get all the benefits I'm talking about. Well, it's better than no life, but you're not going to get all the benefits that I'm talking about if you're just putting bacteria into your soil. So here's the original paper. My husband and I both worked on this paper. It happened, people will look at that Ingham et al. And think that I'm the senior author on this paper, and I'm not. Ingham, R.E., is the first author on this paper. I'm the third author on this paper. I'm Ingham, E.R., which is very confusing for editors. But Ingham, R.E., that's my husband. And so you can see that this is kind of a family thing. Imagine our dinner time conversations. But for those of you who want to go back and look at this, there's the original reference. Please go find it. It's online. It's not that difficult. But from this time, 1986, it's from this time onward, there's been thousands of papers published about this exact same thing, about the exudates, about how many and how often do the exudates come out, what do the exudates control, what's the response of the biology in the soil above ground. So all of the factors that I'm talking about, there are thousands of papers about this. So let's continue on with the example. I've chosen examples from different types of ecosystems. I've got lots of information about grassland work that we've done, pasture work that we've done, lots of examples about grapevines and blueberries and vegetables. We're not going to be here for the next 3 weeks, so I had to pick and choose. So I've tried to pull examples from different kinds of systems. This one happens to be work that was done at the George W. Bush Presidential Center in Dallas, Texas. And the charge to all of us doing this work was to recreate the Texas prairie similar to what was on the Bush Ranch. No ego here. And so these are some of the contributors. Ted Hartzig is the major person who is on this project. James Satillo was part of it, Betsy Ross, Mike Bosco and some of the best compost ever from the Texas worm composting operation. And Earth Fortifications, the SFI lab at Earth Fortifications, did a great deal of assessing the biology in the soil. So I'm not going to bore you in this presentation with tables of data, because that puts most people to sleep. But we have the data every step along the way through this process. Samples were taken so we could monitor what the biology was, so we knew it was always improving. We knew what was not there yet and what we needed to keep adding every step along the way. So if I can have the next slide, I'll go through the visual story of this process. This is the property that we were handed. So this has to become a native Texas prairie within the next year. Notice that down at the bottom right, we started in September of 2013. This used to be a parking lot. They parked every semi-tractor trailer. They parked all of the road equipment. So think about the diesel oil and the gasoline and the toxic chemicals that soaked into this. They laser leveled the land because it's hard for tractor trailers to go over bumps and things. So everything is nice and flattened. And then a layer of gravel on top of it. And this we have to turn into a native Texas prairie, very particular sets of species of plants in here within 1 year. And so we knew we needed biology. All of this has to have biology put back into it. So you can see the huge mountain of compost. We bought every pound of good compost produced in the state of Texas and shipped here. And so this is the first quarter of the compost that we're going to be using at the very beginning. We've got to dig up this soil. If I can have the next slide, I will show you what they called soil. Right. That's not soil at all, is it? That's, wow, those are pretty boulder-like kinds of huge, massive aggregates, toxic chemicals soaked into this is dirt. This is the worst kind of dirt you could ever hope to be stuck with. So how do you turn this back into soil? Anytime in the near future, it takes a lot of compost, a lot of inoculum of these beneficial organisms. So we had to take this was probably about the first 18 inches of support matrix, dirt, and we actually had to roll it in a trommel screen to break this all up and get it broken down so we could mix in the compost, so we could coat everything in these layers with the proper biology and start building structure. Next slide. So the process started, you can remember from the first picture, that the surface of that soil was even with that fence line. You can see Dallas, Texas. This is right on the outskirts. Well, it's actually in the urban zone of Dallas. On a clear day, you would be able to see the downtown section of Dallas. So we're right in the middle of an urban situation. We have to reestablish all of the historical waterways. So the hydrology has to be reestablished. We've got to have proper drainage into a pond. So what you're seeing here is the beginning of the work on the bottom of the pond. This fabric is decomposable by our microorganisms, so we can put it on, have it start the process of holding water in our pond, and then the clays from the surrounding site will sink to that bottom and form the clay bottom of the pond that will prevent water from seeping out too rapidly below that pond. So starting this whole process, you can see how everything looks like it's terraced over on the side. So building in some structural physical support, got to have that to put our soil on top of. You can see the trees that are being planted. So these were all huge root balls. When they were put into the ground, we had the site soil mixed with the compost 50-50. And then right around the root ball was 100% compost, making sure that it was extremely fungal dominated, and we were putting in lots of really good fungal foods so we would support the requirements of those trees. Shrubs, the same way. Perennial plants require fungal dominated. When we started working on this project, almost all the trees on the site that had been planted by previous landscape companies were dead. They were dying. We just had to remove them. So what's going to prevent these trees from dying? We understand the biology, and we make sure that the root systems of these plants are getting the nutrients that they require without pesticides, without inorganic fertilizers, without herbicides going into the system. Once we establish, they're set. We don't have to do anything more to them. So putting in the right biology on the surface. So if I can have the next slide. You can see now we've taken that original, those big clods of pure clay with all kinds of toxic material in them. We've ground them up. We've mixed the compost. So here we are. This is probably January of 2014 at this point. So we've done all the digging through the winter time, through the dormant period. The tree in the right foreground is one that you saw in the last picture. And so all of these trees have gone in with the right biology, and now we're covering that terraced material with the proper ratio of fungi to bacteria in that soil. You can see the pond, where the bottom of that pond is lined with clay. So the stream coming down from the top of the hill is going to feed water into that pond. You can see just the edge in that upper left-hand part of the picture. You can see the edge of the Bush Library as it's being built. So getting all the soil into place with the proper biology for the plants that we're going to try to grow in there. You'll notice that there is no irrigation on the site. We aren't using irrigation because native plants don't do well when you irrigate. That's not the watering pattern that they're expecting. And you will select against most of your native species if you're blindly pouring water onto the site. So keep that in mind. Where's the water going to come from? Oh, and the other thing that was going on was, I believe that the next picture shows us the last rainfall we got in 2016. Texas was moving into a complete and total drought. Of course, we didn't know it at the time. So this rainfall was critical, that we already had the soil down and we got a good soaking rain that replenished all of the aggregate structures. All those little tiny pores in the soil got a good amount of water, 50% moisture going into this soil. So now we have that water holding capacity. These shrubs that you see in the foreground that were planted at this time, they all got completely replenished. Their root system started growing down immediately. So you can see where we put a layer of really good mix of compost, mostly compost with a little bit of the site soil. And so you can see that dark brown organic matter layer that we established where the shrubs went in. Where the grass is going to be planted, so a mix of native grass species being put out on the rest of this landscape. We had the water where the seeds were already there, and the biology in the soil was already performing the function of building structure, so it held that water. A lot of people, when they look at this picture, they see the kind of that aquamarine color that's spread all over everything, and they'll say, oh, that's nitrogen fertilizer. No, that's not. That's kelp. It's a food that helps these organisms grow. Get the bacteria and fungi growing so the protozoa, the nematodes, the microarthropods have something to eat. And we were putting the seed out at the same time. So Betsy Ross was really critical in work she's done in the past, demonstrating that. to people in Texas that works very, very well. So this is the last rainfall that we got. We don't have an irrigation system, or at least not one that worked. So how are you going to keep these organisms? How are you going to grow your plants where you're not having proper rainfall? Well, because we've already got the water in the soil. And it will make the root systems go down very, very deep. So we started out with, these were 1 gallon size shrubs in the foreground. We will watch them grow through the course of this year. So the next slide. This slide with the rainfall was in April, early April. Here we are in September. And look at how those shrubs have gone. This is the exact same location as that previous picture. Look at how much the shrubs have grown on absolutely no rainfall through this growing season. Just on the water that is accumulating in the soil. When the conditions are right for dew to fall, the dew will settle on those leaves, and we will have water running down into the ground. So a lot of the growth of all of these plants was on dewfall. Really important thing to have this plant material in there so that we can condense the dewfall on those leaves and get that source of water back into the soil. So you can see the Presidential Center, the library there, and you can see just a hint of that native grassland that was planted and grew very, very well. Next slide shows that even better. This is down around the pond, and so that riparian grassland, native plants, everything here is a native plant. And so we've got to make certain that we're putting in the right balances of the bacteria, fungi, protozoa, nematodes, microarthropods, setting the stage for this to now sustain itself. No further work was required except for the 3 applications of biology that was done in the early springtime period. Well, we still at least had some decent water. Now, look at the mid right-hand side of the screen. You can see open water in this pond. And this is with no rainfall through the whole entire growing season. So we managed to accumulate in that pond from dewfall water that filled the pond up to about 2.5 to 3 feet in a drought year. Other people have done this in desert systems. I worked with a number of the permaculture people, making certain that the right biology was present to form the structure in the soil. And in stark stone desert, within 1 growing season, we had oasis present, open water, surrounded by trees that survived and grew in what was, a year previous to that, stone desert. If you understand life, you know how to manage this life. Yeah, you got to have a microscope so you can make sure that you're getting this biology into the soil and getting the right balances. So here we have those native flowers growing right around that pond, riparian species. Well, let's look at the rest of this. So keep going. Next slide. We're going to look at another view. Oh, and you can see downtown Dallas right in the background on that. Here's the grassland area. These are native grasses from seed that was put down in April. They rapidly germinated, and their root systems here in September were already 12 inches down into the soil. Today, when you go back and you look at the grasses that are growing here, their root systems are well below 6 feet. We want those root systems to go down. That's what they're supposed to be doing. But you cannot be compacting the soil. You can't be going out here with big equipment. Or if you are coming out and mowing, and yes, they're mowing here, you're going to have to treat those mowed trails with the proper biology injected into the soil down below the point where the compaction is forming. Well, how do you tell where the compaction is forming? Well, it's you take your penetrometer and you push that penetrometer down into the soil, and you find out where you have to push so hard that you can't push that metal rod through the soil. There's your compaction layer. You got to get down below that and inject these sets of organisms into that soil, so you reestablish soil instead of dirt. So next slide. No invasive species in that prairie. Here's another picture from where one of our trees was planted. No pesticides were used, no inorganic fertilizers, no irrigation, no weeds. The Lady Bird Johnson Wildflower Center sent people out because they did help us pick the right seeds. They told us how to make certain that those seeds would germinate exactly what we wanted to have in that soil for those seeds. Of course, me working with them saying, here's a balance of the fungi, bacteria, protozoa, and nematodes that we need to get these native species to germinate, grow, and start putting those root systems down into the soil. So all of those things, no weeds in that system, only what would appear in a native grassland. So they sent people out to classify how well did we get the percentages of all the different grasses and forbs and herbs and trees and shrubs. How well did we do in reaching that goal? And we got an A++ rating. It was perfection as far as they were concerned. Managed to do it all. But you have to understand biology. You have to be monitoring and making certain that things are going the right direction if you want to be finished in a year, if you want a success story within that year period of time. Now, if you want to kind of fool around and, take a number of years, okay, you're going to have to be paying attention to your plants. Your plants will tell you what's going on. But by the time a plant's dying, you're going to have to wait till next year then to try to continue that process of fixing the system. So next slide, please. Moving on, I believe, to a different example. Another example that's showing, now this is work that we were doing with Hendrika Schraven up in Washington State, just outside of Seattle. And in this one, we were challenged that roots of grasses don't grow more than maybe 2, 3, 4 inches, 6 inches max is as deep as grass roots will grow. So we set up a bunch of plots where, yes, we compacted the soil, we treated the soil exactly like you would in an urban situation, and yeah, the root systems of those grasses don't go down more than 4 to 6 inches because there's your compaction layer imposed by all the equipment, by all of the compacting that goes on when you're establishing lawns or lawns around a building especially. But then right next to that, we made certain that that compaction was alleviated by mixing in the right organisms in compost. So that whole mix of all of the diversity of all of the organisms mixed into that soil. We injected compost extract down into the soil, so we made sure that that whole profile had really good biology in that system. Seeds on the top, so these seeds were put on in a mix of compost to which we had added foods and the seeds. Put out on the surface, I think if I remember correctly, it was about a 1/4 of an inch layer with the seeds and all that good food and all the right biology. And so the roots started growing. These were planted, the seeds were put into the system on July 15. This is harvest on November 6th. So we've looked at, July 15 to August, September, October, and right at the beginning. So 3.5 months later, we put a cylinder, punched a cylinder, PVC pipe, all the way down to 4.5 feet, lifted that cylinder with that turf intact, and all of the root systems going down 4.5 feet, lifted it out, took a saw and opened up that PVC pipe, washed the surface of the soil off, took the soil out with just a hose, gentle hose, and here's the root system. So tell me, how far down do roots of grasses go? And this is your standard ryegrass. This is the stuff that most people use to plant their lawns. No weeds in that system, no diseases. Yes, we had to mow it. I do like to point out that this grass was mowed to 1/2 inch twice during the growing season. The second mowing was just a week before, a few days before. We pulled the core out and took a look at this. A lot of people say, here's some more mythology. A lot of people say that when you cut the top part of a plant, it causes the root systems to fall off. Absolutely not true. The person who first started saying this has admitted that they're wrong. You cut the top part of a plant only if that plant is sick, only if it is unhealthy to the point of death will the root system fall off. When you're so sick, you're barely staying alive. Might you lose your limbs? Might you lose your hair? Any living creature has that response when they're that close to death. But if you're healthy, if these plants are healthy, you cut the top part of that plant, all you get is more root growth. Because the plant's got to put out exudates to get the nutrients sequestered in the bacteria and fungi growing around all of those roots, attract those protozoa, those nematodes, those microarthropods to come in, eat the bacteria and fungi, and feed that plant with all of the nutrients that that plant has to have to regrow the above ground part of that plant. It's not just carbon that goes into plant material. It's every nutrient required by that plant has to be taken up through that root system. You have to have this nutrient cycling going on. If you're putting nitrate fertilizer out on a plant, where are you getting the phosphorus, sulfur, magnesium, calcium, sodium, potassium, iron, zinc, boron, all of those other nutrients? You're not improving those. So where do they come from? You better have the biology in your soil. Okay, let's keep going. Next slide. There we go. So a slightly different system. Now we're getting into vegetable production. This is work that Daniel and Caitlin MacLeod did in Petaluma in California. We were starting to work with them. They wanted to check out and make sure that this whole biological system was actually working. Could they monitor the type of biology that's present? So they planted this whole row of chard, Swiss chard, without any additional biology in it. The chard started to come up. And then the front half of this picture, they sprayed with one application of a really good tea, so that they knew the biology that was in the compost. They could make sure they pulled that biology out of the compost and into the tea, grew up the number of organisms to high levels, and then they applied that tea to the front half of this row of chard. And this is 1 week later. Tell me, does adding biology improve the growth of plants? And we see this over and over. They got much higher production levels. They didn't have the disease. They were not getting the aphid, the white flies, no attack by the diseases of pest organisms on the chard that they applied the biology to, whereas the other portion of the that row of chard was having some serious problems with pests, especially the white flies, the aphids, things like that. They were having some diseases. You can see some evidence of that disease problem starting to develop in that as you look at that back half, you can see some yellowing happening. People have this odd idea that it's normal for plants as they grow, the lower leaves get brown, they get yellow, they get brown, they curl up, they dry up, they fall off. They think that's normal. Mother Nature is trying to send you a message. She's trying to whack you upside the head and say, pay attention. There's something terribly wrong with this plant. Something's lacking. You need to fix it. If you want good, healthy food to eat, you better fix this problem, or you're not going to be getting the nutrition that you need in order to stay alive. So let's keep going. If we can move on to the next slide, because there's a number of these things that I want to look at, different systems. This is work that we did in Australia with table grapes. This was, again, a year where it was a terrible drought. Well, really, when you want to go back in the records, Australia up to this time in 2006, 2007, had suffered about 35 years of drought, where they were not getting normal levels of rainfall in that eastern central part of Australia. It's perfect for growing grapes, but you do need some water. So with this particular company, they had about 35 farms that range all the way from the tablelands up in the northern part near Darwin in Australia, all the way down through the continent to Melbourne. And they have table grapes all the way through. They had one farm that they'd never gotten a production of grapes because of all kinds of different problems. The vines were stressed. There was problems with insect pests and problems with nutrients, and just we asked them if there wasn't a farm that we could demonstrate that this biology works and what's possible for them. Well, we're not sure. You don't have 20 years of scientific data behind you. No, we only have 4 billion years of Mother Nature evidence behind us. But okay, so give us this farm. You're not going to make any grapes on it with your particular agricultural practices, so let us take over. And this was a year that was extremely hot. I mean, the drought was really painful. There was no water in the dam. There was no rainfall. Nothing was replenished in that dam. And yet, because we went out and we put a good couple inches of compost on the row where the grapes were growing. So I'm trying to get this into the picture. So the raised bed or the raised area where the grape was planted, we made sure all of that had a really good layer of good compost with all the proper biology, and we kind of mixed it into that soil through mechanical means. When you're laying down that compost, you can churn up that soil just a little bit. They would French plow the grapevines, put the inorganic fertilizers down, and then push that. So there were no surface roots in that row of raised soil, raised dirt when we got to it. So we put the compost out, and then we applied 3 applications of compost tea. When we saw insects or diseases starting to colonize some portion of the production and wherever it occurred in the field, we were out there the next morning applying that compost tea, making sure that we got rid of all of those problems, protecting those leaf surfaces. If a plant is stressed, it puts out substances that go off into the atmosphere, gases, and insects have learned to home in on those signals. And they've learned that that's going to be a weak, unhealthy plant. And so the insects have very little trouble attacking and harming that plant. Well, and of course, if you've got a plant that's sick and there's your source of insect pests, well, then they move out. When insect pest numbers are so high, even healthy plants are going to lose it. So you've got to be watching right from the very beginning for any evidence and make sure that you get that plant covered so that no more of those gases, though no more of the signal goes out from the leaves, from the bark, from any portion of that plant, from the blossoms or the seed set or the fruit, if you're that far along. You have to make certain that that plant gets healthy, which means you're going to have to do something about down in the soil. You've got to put this biology back into the soil. So with grapevines, you can't be digging them up. So you inject that biology down into the root zone, and you want to go as deep as you possibly can. The depth of the rooting of these grapevines went from about 6 inches down into about 10, 15 feet within one growing season. You can see some of the data. This non-productive farm achieved normal yields in 1 year. This happens because this particular year, severe drought none of the other farms produced. This was the only farm. So the next year, they converted all 34 of their farms. Another severe drought year, but production occurred. So they had a lot more yield. We saved the company, basically. So what's the cost of that? Having a company that grows grapes and sells them or not. They reduced operating expenditures by 16%. There's your pesticides, there's your inorganic fertilizers, there's all that sulfur spray going out. Yeah, breathe that sulfur. Kill yourself. Improved fruit quality and reduced water use by the grapevines by 50 to 70%. Once again, these grapevines grew on dewfall. We didn't have to have a dam full of water because enough dew, condensation, because of difference in temperature, the water in the morning would condense on the surfaces of the plants and drip down into the soil, and that was enough water to keep these things growing. A lot of times in the evening, you'll have dewfall. So we've got to conserve these things. You got to really understand how all of this system works. Next slide. So when we're looking at all of these examples, we really want to make certain we're doing everything to get all of the benefits that I first started talking about at the beginning of this conversation. So now we come to what we're doing here on the farm in California. We're just a little bit north of Oroville in California. We're like 2 valleys over from Tahoe. So Tahoe, Grass Valley, and then here we are, just north of Oroville. We're up at about 3,600 feet. So it's maybe not as hot here, a couple degrees. That's all that adds compared to the valley floor. So in this particular experiment, we have an agricultural field that had been, the previous owners had just overdone it with Roundup, trying to get rid of the weeds, trying to beat back the ferns, beat back the kinnikinick, beat back all of these weedy species. And the residues of Roundup were just incredible in this soil. So we've got that particular problem. Roundup immobilizes any soluble nutrients, sucks it right up, and holds it on the surface of the Roundup, on the glyphosate. And so it's no longer available. So, when you use Roundup, you're going to have to use inorganic fertilizers. So that's what we're dealing with here, this is a normal agricultural field, if you will, because all of these toxic chemicals are not decomposed in this soil. So here is half of the field. You can see we've got drip irrigation in there. We've planted plants. The row in the foreground, we've taken out all of the lettuce, and I'll show you the data from that lettuce in just a little bit. But we're looking at a row of peppers. They're the things with the little tiny green guys on there. The peppers are just coming along. And, it's not bad, but you have to realize that this is mid-August. And we're just starting to see a pepper crop come up on this half of the field where no additional biology has been added. We've put on mulch. We've done all of the things that you would normally do in growing plants. It's just that we have not added compost. We have not added compost tea or compost extract. No additional biology. And then, of course, I'm going to show you the other half of the field where we added that biology. We put on compost. We put on compost teas. Whenever we start to see a problem in the other half of the field, we'll go out there and spray that particular plant, that particular problem, and get rid of it. Whereas on this side, the only thing we could do to get rid of, the aphids, get rid of the whiteflies, try to deal with things was to blast the creatures off of the plant and hope that by squishing their little bodies, they wouldn't come back. Well, yeah, how well does that work? So typical conventional agriculture on this side, and then I will show you what happens when we add biology. But this gives you a good baseline of what would be the production here. So we're looking at peppers in that first row. The next row is cucumber. We've got a couple of plants that are growing pretty well, but for the most part, a little bit behind. The third row that you can just barely see the end. I'll show you a better picture of it. We've got okra growing in there. Then we've got 2 rows of tomatoes, 2 different varieties of tomatoes, heritage tomatoes. And then the corn back there. So we've got 3 rows of corn. On that corn in the back, you can see that a few of the stalks have tasseled. Most of those corn have only 1 ear on them or no ears. They haven't gotten tall enough. They are stressed for lack of nutrients. So what do we have to do to bring that production back? So let's look at one more thing I want to point out to you before we look at the with biology is we've tried to grow cover plants here in order to prevent evaporation from the soil. Now that's not exactly normal conventional agriculture, but you know, water is limiting in California, and we can't be spending that much on the water bill, bad enough as it is. So we want to make certain that we are retaining and holding as much water as we possibly can. So we significantly reduce water loss to the atmosphere by having this green growing layer. Very short, low growing green plants. They're going to be slightly different cover plants for every part of the world. We've got to do this testing to see what are the best cover plants that will protect your soil and not lose water. Imagine if these cover plants weren't there. Imagine if we had just herbicided everything here. Think of the evaporation loss every second of every day. And we had many days this summer that we were well over 100 degrees. So what would our water bill have been without that protection? So we are trying to do that regardless of what we're in the without biology or the with biology part. And I'll show you some more results on that as well. So the next slide is all I'm going to do is shift and take a picture that way. And there's our different rows of plants with biology in the system. You can see all the peppers are doing better on this side of the field, not a huge amount better, because you got to remember that peppers are fairly early in succession. They do pretty well with a strongly bacterial dominated food web. We are getting more fungi in there. We have improved the biology, and we are seeing more peppers. You can see that most of these plants have peppers on them starting to grow, as opposed to that last picture there where we only had peppers growing on, well, half maximum. The next row then of cucumbers, you can see that the cucumbers are almost all the way up to the top of that 5-foot fence that we're using to trellis. The next row is the okra. You can't even really see the okra from here because the cucumbers are growing so much better than in the without biology half of the field. Beyond that is 2 rows of tomatoes, and they are all trying to grow. Those tomatoes are already up and trying to grow higher than the 5-foot fence. And then beyond that are the rows of corn. And every single one of the corn stalks have fruited. We have 1 to 2 ears of corn on every stalk. So much better production, much healthier plants. And of course, you can see that those cover plants are growing really well in the system as well. So an example from research where we're very carefully controlling, this gets the biology, the other does not. And so which half of this field is the half that you would want to have for your production system? So the next slide, I think a couple more examples from the farm here, where we're going to look at, here's the okra. You can see how well the cover plant is doing where we have biology in the system. You can see how much better the okra is growing. We'll look at the without biology on the other side. You can see to the left-hand side here, we're looking at the squash. So there's a row of squash in here that I forgot to mention because I couldn't remember what was there. You can see how well that squash is going. We've already harvested quite a bit of the squash from that production area, that row. You can see the tomatoes on the other side, and lots of tomatoes coming along. This was mid-August. We have more tomatoes than you could possibly imagine right now that we're selling. The okra is doing really well, so quite a bit better, and I'll give you yield data. Not for the whole year, of course, because we haven't finished producing, but I'll show you the difference as of the August harvest date. So when we're looking at weeds in these systems, we, on rare occasions, will have a fern or two that we have to weed from this row of okra. What we try to do is leave the system alone. No weeding for a week. Both sides, both the with biology and the without biology side, and then come back in and measure the time that it takes us to weed whatever's come up in the no biology as compared to the with biology. No biology, it takes us 10 minutes. Absolutely. You know, we're pulling 3 or 4 weeds. That's it. On the other side, without biology, it's taking us half an hour to 45 minutes. Because we've altered the food web, we have an improved balance of fungi to bacteria, protozoa, and nematodes on this with biology part of the system. The weeds don't grow. The kinds of nutrients that they need, the form of those soluble nutrients is different. It's the biology selects for the growth of the plant we're trying to grow. We're getting the balances correct for this plant. Whereas on the other side, we are not seeing that kind of improvement. So cover plants, the okra, the other plants growing very, very well. Now let's just turn around and take a picture going the other way and see what the growth of the plants without added biology looks like. Next slide. There we go. So there's the okra without added biology. Note that the cover plant's not doing very well on this side either. You need the biology to support the nutrient cycling, to make those nutrients available. You know, the first time you irrigate, and this is drip irrigation, and that drip irrigation goes for several hours every day. All the soluble inorganic fertilizer that might have been put on here, those soluble nutrients are gone. They're going for groundwater. They're going to be washing into your rivers and lakes and streams. Maybe not this year, but that's where they're going because there's nothing to hold them. Plants start growing, yeah, but unless you're constantly putting on inorganic fertilizers at very low rates, and who's got the kind of time to do that? So you can see that the okra is not doing all that well. Again, to the right-hand side this time, you can see the squash. And the height of the plants is nowhere near what it is with the biology side of it. We have not picked much yield from those, from the squash. Look at the tomatoes on the other side. You can see all the way through back down into the peppers because the plants are not growing that well. They're stressed. The tomatoes are all small. This is what biology does for you. So you don't have to work so hard. We're getting evaporation off the surface of that soil, and so we have to water more to balance the loss of water off into the atmosphere. Next slide. I think I'm coming to the end, which is just about the right timing. I think the last half hour of this is meant for discussion, questions, and such. And so where this is my last slide. We've got a couple more about the classes and things. But here is the yield of these different crops. Now remember that I've put the harvest date, so you can see that we're only part way through production. Now the carrots, that is the whole production, and we're looking at, with biology, what was the weight of the plant material that we harvested from a 10-foot length of row. 3-foot wide bed, so we have 2 rows of the plants growing in each of those beds, and so we're taking it from 10-foot sections. So with the corn, we haven't actually harvested yet, but each one of those stalks have 2 ears. Here we are about a month later, September instead of August. Some of those stalks have 3 ears. As compared to where we don't have the biology added, there's only 1 ear per stalk. So harvest is going to be much, much higher where we've added biology. With a kale crop, look at the difference between where we have biology and where we don't. And this is the first picking from those kale plants. Comparison of 2.5 pounds in 10 feet of row as compared to only an eighth, 0.8 of a pound where we did not add any biology. Look at the difference. What do you want for your own production system? It doesn't take as much work. You don't have to put so many amendments, and you're increasing yields. If you calculate this the way most agronomists would calculate this, that's a 300% increase in yield. In radish, 2.2 pounds as opposed to 0.1 pound. That's an increase of, whoa, huge amount of improvement in yields, harvestable yield. Mixed lettuce, it's interesting to me sometimes where we're dealing with very early successional plants that like very bacterial dominated systems, we don't see as much of a difference. So the difference between 2.1 pounds as compared to 3.5 pounds, well, that's still significant increase. But it's the later successional plants, the things that require more fungi, that really need mycorrhizal colonization on the root system, are doing better. There's a cucumber, same thing, 2.1 pounds. With biology, only 0.8 pounds, not even a full pound, in a 10-foot length of row. And carrots, 5.4 pounds as compared to 0.6 pounds. Huge difference. So these are the types of things that we want to continue doing at the farm. We're going to continue expanding our agricultural area on the farm. Right now we probably only have about 5 acres in production. It's a 60-acre farm. So we have plenty of room to expand and keep doing experiments to show what this process, how much is it going to take. I do want to point out, with all of this work that we've done so far in the first year of us being on this farm, first full growing season that we've been there, all of the compost, all of the extracts were put on the surface of the soil. My first question was, do we really have to work so hard? Do we have to go in and till that compost into the soil? Do we have to do that work to get that biology spread all the way down deep below the compaction layers that might be there? And so everything was just put in on the surface. The biology in these systems have only moved down the first inch. But look at the effect that it's having on the plants. The plants are gaining benefit for all that good improvement in nutrient cycling, in disease suppression, in holding water. All of those things we already talked about are happening in the top inch, and look at the effect on these plants. So do we have to go in there and till it all in? Well, in the work that we're doing on the farm, we have now started to another set of plots where we have tilled all the way to below the really tough compaction layers, and we're going to have data on how much improvement in yield do we get as compared to when we just put the biology in on the surface? How long is it going to take for these organisms that we're putting on as compost layers, that we're putting on extracts on the surface of the soil, just spraying it on? How long is it going to take for that biology to work its way down year after year? How long until just surface applications take care of the whole problem? And now our roots can grow down without being encumbered by compaction layers. Well, the roots are growing down deeper, even though we're maybe not seeing a massive increase in the biology as we go down in that soil. So all these kinds of questions. We want to be looking and answering those kinds of questions. What if, and here's something we're going to do next year, what if we go in there with just a full bore application of let's get all the compost in there and let's get it deep down and tilled into the soil, and then we're going to come along with the compost extract, and then we're going to come along with all these organic fertilizers that are foods to feed the biology, to move them along in the right direction much, much faster. We need to have that microscope so we can tell which organism has established, which sets of organisms have established and really started growing, doing all of their thing, but who is still lacking? When we put out the next compost tea, should we still be selecting for fungi? Or is it really the protozoa that need more help? Or is it the nematodes? Or is it microarthropods? Let's spend the time on our compost and in our teas to enhance the organism that's still missing out in the field. So I think the next slide is going to talk a little bit about learning to restore your soil. I have just given you a brief, bare overview, the tiniest introduction to all of the things that you want to learn about when you're dealing with different crops in different parts of the world, in different kinds of ecosystems. How do you modify this management for a tropical rainforest? How do you modify this for the Saudi Arabian desert? How do you work in the grasslands, the savannas of South Africa or Zimbabwe? What happens when you're in Australia and Darwin versus Melbourne, or you go to Tasmania? What happens in New Zealand? What are the differences? What do you have to pay attention to? We've been there. We've done work in all of those places. I think the only continent I haven't managed to get to is Greenland. Most people don't grow crops in ice. So I've got experience in all these different kinds of systems. And how are you going to get the biology into your soil and then make certain that you enhance and keep it all moving and growing with the least amount of work from a human being's point of view? Put your willing organic workers back to work for you. You just have to make sure you get them into the soil and you give them things to eat. In this picture that's on your screen, this is it's a calendar that's put out every year by the Lexicon of Sustainability. Really great sets of calendars that they've had over the year. I happen to be their very first picture of their very first calendar. The January issue, gosh, I think this has got to be 4 years ago, maybe 5. So I was really pleased to be the first, the January poster child, and start working with us. The next slide is going to be about some of the classes that you can take, and this is that exclusive offer. For those of you who attended this webinar, we've reduced the price by $1,000 for the Life in the Soil class. And this is the basics. This is understanding which of these organisms do what jobs, which are the ones that you want to have, which ones are the indicators of, uh-oh, something's wrong in your soil. So you can always stay right on top of growing your plant and getting maximum production in the shortest period of time for the least amount of work and the least amount of cost. Let the critters do the work for you. If you kill the critters off, then you're going to have to do their work. And that's expensive, and it's not a lot of fun. Unless you really like driving your tractor back and forth across your field, compacting the living daylights. If you like sending all your money off to those chemical fertilizer guys, okay, then stick with it. Otherwise, start learning about this biology in the soil and how we can change and select for the plant that you want to grow. Lots of information in the Life in the Soils class about the organisms and what they look like. The poster behind me is from that class. So we go over all of these different organisms, who are the ones that you want for what kind of plants, under what conditions. So you'll be able to understand all of that. The next slide shows the practical classes. So we have a class on compost. If you want to make your own compost, how do you do it and make certain that you've got all the right sets of organisms in that compost? Remember that in your soil, you have to have all these airways and passageways to allow water to move through, but also to allow oxygen to move in to your soil. If you don't have enough oxygen exchange, if that's restricted by a compaction layer, or you don't have good structure in that dirt, because if you have organisms, you're going to have structure. If you don't have organisms, you're not going to have structure. That's going to be dirt. You've got to have those air passageways. You've got to have that oxygen moving down through. It must be aerobic. So your compost, where you're growing the organisms to put back into your soil to get the biology to help your plant, had better be aerobic as well. So how do you do that? Well, and not just one kind of composting. There's thermal composting, there's worm composting, there's static composting, there's kind of the backyard homeowners, put your waste into the pile composting. So we go over all of those different ways and trying to help you understand where you find the inoculant, where do you find the organisms, to make certain that you're getting the whole food web back into your pile. The compostee class. So if putting out a solid material is going to be too expensive or too laborious for you, you can convert your compost into a liquid form. So should you be using compost extract or should you be using compost tea? Which one is it? And so we go over those kinds of considerations. How do you make that compost tea? Do not let it go anaerobic, because when you go anaerobic, when anaerobic conditions prevail in anything, your nitrogen is going to blow off as a gas. Oh, good luck growing plants with no soluble nitrogen in the system. Your soluble phosphorus, your phosphate, is going to blow off as a gas under anaerobic conditions. Your sulfur is going to blow off as a gas. How can you grow plants with no soluble sulfur? How are you going to replace those inorganic nutrients that you just happily let it gas off? Only under anaerobic conditions are the really strong acids being produced. Anaerobic metabolism releases really strong acid materials, things like acetic acid, butyric acid, things that tend to stink really well too. So think about butyric acid, the smell of rancid butter or sour milk, only produced under anaerobic conditions. The vomit smell, oh, wonderful topic here, isn't it? Anaerobic conditions, where you produce putrescine, the smell of decaying flesh. Now, how many of you have walked outside and it's like, whoa, who's got the dead fish? What's causing that anaerobic odor? Some really toxic organic acids. And if they get anywhere near your root system of your plant, you got a dead plant. So going anaerobic. Oh yeah, you got lots of microbial growth, but the wrong microbial growth. You're losing the biology that you need to help your plants. So how do you know that things are going anaerobic? How do you know? Well, again, microscope. The organisms in your soil are much faster at responding to slight changes in conditions. And so by looking at that biology, you'll be able to tell instantaneously. So, oh, but I'm going to have to learn how to use a microscope. Well, we have a microscope class. So we will help you Learn how to use these small microscopes. The microscope only costs about $300. If you want to put a fancy camera on it, you can do that. That's going to cost you, 50, maybe $100 more. But the microscope by itself is about, well, it depends, $250 to $300. And we have recommendations for where to go find those microscopes, order them, get them. Um, so you can learn. It has to be a shadowing microscope. So your standard classic light microscope with an Abbey condenser on which there is um, a slide that you can shadow the organisms in your sample. So you're making a compost tea. You're going to take a little bit of your compost, dilute in a little bit of water, shake that up. A drop of that goes on the microscope slide, cover slip on the top of that. On the stage of your microscope, turn the light on, you look through there, and you can say, whoa, there are no fungi in here. There are no protozoa. There are no good guy nematodes. All I got are bad guy nematodes. It's that fast. It's that quick. It doesn't, you don't have to sit there and count everything and measure unless you want to quantify. And for scientific purposes, we quantify. So we usually teach people the whole meal deal, how to quantify these organisms as well as just get a good general idea of, oh, there are no fungi at all. Or you go, look at all the fungi, look at all the protozoa zooming around. This is, yep, that's what you want to see. Well, it is relative to the plant you're trying to grow. So for all four classes, instead of paying $5,000, you're going to pay less than half. So though that's the deal, that's the offer for you having come to this seminar. Listen to me hold forth for a couple hours here, and I think that's the last slide. So it's been very enjoyable having this opportunity to chat and talk to you about my passion in life, my favorite things to work on. I'm a research scientist more than I'm anything else. So I've turned over most of the business end of these things to other people so I can concentrate on the research. It's so much more fun. So back over to you.
Hey, everybody. Thanks so much for watching this video with us. This was a replay, and we'll be back next week for the second part of this video, which is a Q&A session. And those of you who are watching this on YouTube, please hit that subscribe button, like us, and share this video if you're on Facebook. Also, go to our Eat Community website to find more videos. And I see that Alicia has put some information into the chat. So there's green wall of mangrove video, blue carbon video, lots and lots of good stuff. So thank you so much, Alicia, for those information in here. Robert says, great to see mangroves being established. Thanks. All right. Um, great presentation, says Alicia. All right. Thank you so much, guys. We'll see you all.